In today's class, we considered the motion of a point along a curve. The vectors you see here are position vectors, and we generally will use, I just had a piece of chalk. We generally will use R of t for position vector, and that'll be x of t I plus y of t j for motion in the plane. And if we're moving in 3 dimensions, we can add a z of t times the k vector, bringing us out of the plane. I've drawn a series of r vectors, and with the tacit assumption that these vectors represent the positions at equal time intervals. So the particle is here, after some time it's here, after an equal time interval it's here, after another equal time interval it's here, and after another it's here. These vectors all originate from some common point, which might well be the origin of our coordinate system or the pole of a polar coordinate system. We have an x-axis here, and we could have a y-axis. I haven't drawn it. Now, we've sketched intermediate points. We've sketched points at the end of each of the vectors that are represented here, and then intermediate points that are going to represent the successive positions of the particle at equal time subintervals, equal intervals that would be 1/3 of the interval between which the r vectors were drawn. So now we have kind of an idea of how the object moves, and your class was asked to determine how many times the object slows down, then speeds up. Okay, well, we see that we move pretty far here, not as far here, but then further and further. So we have a slow down, speed up cycle here. We have another one, we slow down here and then speed back up, and then we slow down and then speed back up here. I see 3 slow down, speed up cycles. If you were to graph speed versus time, the graph might look something like this. And that's just a very approximate graph. It doesn't even have the required number. I guess it does. Slows down, speeds up, slows down, speeds up, slows down, speeds up. Now, another question you were asked to respond to, or the class was asked to respond to. How many times does the direction, or where does the direction of motion change most quickly? And I asked that be specified by the angle of the r vector at the time when the motion changes most quickly. And the question came up, we're talking about the rate of change of the motion with respect to distance along the curve or with respect to time. Now, most of the class, but not all, is taking a differential equations course, a multivariable calculus course, and that is a very relevant question. Okay, so without going into the multivariable calculus detail, we'll say with respect to time. Okay, quickly, generally is going to refer to time, although not necessarily. But if it refers to anything else, we do need to be specific. If we just say quickly, we're going to be talking about with respect to time. So ask that to be specified by the angle of the r vector at that point. So if you think that that's happening down here where the curve is changing, where the curvature is greatest, then you would probably say something like around -15 or 20 degrees. If you think it's changing up here because the velocity is greater, even though the curvature is less, then you might say 40 degrees or something. Okay, now I brought it up, so let's discuss it. You're going to be changing direction more quickly. There are 2 effects. There's the curvature of the curve, and if you're moving with equal velocities at points of 2 different curvatures, the point where the curvature is the greatest, where the magnitude of the curvature is the greatest, will be the one at which your direction of motion is changing most quickly. If, however, you're moving at different speeds, if you're moving faster on a curve of, at a point of less curvature, as opposed to more slowly on a point of greater curvature, then you have two opposing influences, and you have to balance those out. And the idea was not to balance those out in terms of this picture. You probably wouldn't be able to estimate that very well. With little practice, you could. But just to raise the question, okay, of how the speed and the curvature combine to make the direction of motion change most quickly with respect to time. Now, that's indicated up here. Up here we have greater speed but less curvature. Down here we have greater curvature but less speed. Now, I then asked that you sketch, or that the class sketch the velocity vectors and estimate the magnitude and angle at each point corresponding to the endpoint of one of these r vectors. Now, actually, I take that back. I said at this point, this point, this point, this point, and this point. Now, I drew the vector for this point. It's going to be tangent to the curve for all the reasons that you should understand. And I put a scale on it. I said, okay, let's say the velocity is 10 here. I didn't put units on the velocity. We're just talking about relative numbers. We don't otherwise have a scale on this diagram. We're trying to get a handle on the concept. So when I sketch the vectors, they look kind of like this. Hopefully you can see those. There's one here, one for this point, and one for this point. I asked the class to enter the magnitude and angle of each of those vectors. The first one may be at of magnitude 10 at what looked like maybe 25 degrees, angle in degrees rather than radians in this case, for no particular reason except degrees are easier for most people to estimate. And people came up with reasonably good estimates. We see that the velocity vectors appear to be getting progressively shorter. And most estimates came out with a decreasing number here on the velocity coordinate. And the angle seems to be, at least for this segment of the curve, progressively angling downward away from the positive x-axis in the negative direction. So the angles went from like negative 25 to close to negative 90 degrees down here. All this is just to get a handle on what we can see in the motion from this information. I then asked that we estimate the average velocity for each interval, like between A and B, between B and C, between C and D. And since the velocity is not changing linearly, you can't really get the average velocity by adding the two velocities and dividing by 2, but that's the approximation we're going to make, and we're not going to be too far wrong if we do that. So average velocity is defined as average rate of change of velocity. I'm sorry, I'm making that common mistake. Average velocity is, this is completely wrong. Okay, I wrote this completely wrong. I think I actually just put this symbol wrong because what I was getting at was the change in velocity. And actually what we're calculating here is the average acceleration. A little bit of an embarrassing mistake there. Average acceleration would be the change in velocity over the change in time. Okay. Anyhow, we want to get the change in velocity. This is the point. We want to see how the velocity is changing, and that's really the focus here. And we'll get to acceleration shortly. So how do you get the change in velocity? Well, the change in velocity between A and B is just the velocity at B minus the velocity at A. So if we take the vector for the velocity at B, which we represent over here and the vector for the velocity at A, which we represent here. And these being vectors, we can move them together so they have the same initial point, and we want to do that so that we can easily get a picture of the change in velocity. Okay, there are two ways to do this. We can take the vector VB and subtract the vector VA. Minus the vector VA is just a vector in the direction opposite VA, having the same magnitude. So here we have VB, and we put that head to tail with negative VA, the vector is equal and opposite to the VA vector. And then when we go from the initial point to the final point, to the terminal point, we get the vector VB minus VA. And I didn't label that, and somebody's moved my chalk, which is all right. Somebody else was in here with valid reason to do that. But okay, here's VB minus VA, the vector VB minus VA. Another way to say it is that VB minus VA is what you add to VA to get VB, because if you do VA plus VB minus VA, I'm sorry, if you do VA, I don't know if I said that right, if you do VA plus VB minus VA, you get VA. You get VB. If you add this to this, you get this. So the vector that you have to add to VA to get to VB is the vector delta V, or VB minus VA. So that's the delta V, running out of room here. Delta V AB, you probably can't read that. Graphical representation of the delta V vector. Okay. Now you can do the same with vector BC, vector CD, vector DE. Using the vectors I see here, these are my approximate sketches. I've offset the difference vector here, the VA, the VB minus VA vector, just so you can see it more clearly so it isn't cluttered up within the heads of the other two vectors. Then, if we want to do the average acceleration, we can divide the delta V vector by the delta T interval, whatever that interval might be. That is, of course, going to change the units of the quantity. That's not going to have the same units as delta V. So we could sketch it on any scale we wished if we wanted to sketch the acceleration vectors. Now we'll go on with this in a minute.